Welcome, I'm teacher Ivan from WANA Educational Services. Today we'll uncover how radioisotopes act as invisible detectives, helping scientists solve environmental mysteries and protect our precious planet's future. Have you ever wondered how scientists are able to track down the sources of pollution in our rivers, the air we breathe, or even the soil beneath our feet? It's a complex process that combines fieldwork, advanced technology, and a bit of detective work. Environmental researchers venture into the field, collecting samples from water, air, and soil, searching for clues that can reveal the presence and movement of pollutants. In the lab, radioisotopes such as tritium, beryllium-7, and iodine-131 become powerful tools. These substances act as invisible tracers, allowing scientists to follow the journey of contaminants through the environment. By detecting even the tiniest amounts of these isotopes, researchers can uncover where pollution starts, how it spreads, and where it ends up. Using sophisticated mapping and data analysis, experts can visualize the movement of pollutants over time. This helps them understand how contaminants accumulate in certain areas, identify hotspots, and develop targeted strategies for cleanup and prevention. The information gathered is crucial for protecting both ecosystems and human health. Thanks to the use of radioisotopes and ongoing environmental monitoring, we can keep a close watch on our natural world, even when the signs of pollution are hidden from view. This science helps ensure that our environment remains safe, healthy, and protected for generations to come. Radioisotopes also let us time travel. Carbon-14, lead-210, and cesium-137 help scientists date ancient trees, sediments, and artifacts. By reading isotope layers in mud or wood, we reconstruct environmental history, fires, floods, and human impact. These atomic clocks reveal how our actions shape the planet and guide smarter decisions. Without radioisotopes, our environmental timeline would be a blur. Radioisotopes play a vital role in unraveling the complexities of climate change. By studying different forms of carbon, such as carbon-12, carbon-13, and the radioactive carbon-14, scientists can trace the journey of carbon atoms as they move through our planet's interconnected systems. These isotopes act like unique fingerprints, allowing researchers to follow carbon as it cycles between the atmosphere, oceans, plants, animals, and soils. By tracking these isotopes, we gain a clearer picture of how carbon is exchanged in nature, between forests, rivers, oceans, and the air we breathe. This helps us understand the natural balance of the carbon cycle and how it is being disrupted by human activities such as burning fossil fuels and deforestation. Analyzing isotope ratios in air, water, and biological samples allows scientists to pinpoint the exact sources of carbon dioxide. They can distinguish between carbon released from natural processes like volcanic eruptions or plant respiration, and carbon that comes from human-driven sources such as coal, oil, and gas combustion. This detailed data is essential for building accurate climate models and informing policy decisions. It provides solid scientific evidence that guides governments and organizations as they develop strategies to reduce emissions and protect our environment for future generations. Thanks to radioisotopes, we can visualize the invisible impact of human activity on our climate, making it possible to measure changes over time and take meaningful action to address global warming. How do we know where groundwater comes from, and how can we be sure it's safe to use? Groundwater is hidden beneath our feet, flowing silently through layers of rock and soil, making it difficult to observe directly. Scientists use a variety of advanced techniques to monitor and study these underground reservoirs, ensuring we understand their origins and behavior. One of the most powerful tools involves using natural isotopes like tritium and carbon-14. These act as invisible tags, allowing researchers to determine not only where the water came from, but also how long it's been underground. By analyzing these isotopes in water samples, scientists can estimate the age of groundwater with remarkable accuracy. This process, known as groundwater dating, helps track the movement of water as it travels through different layers of Earth. It reveals how quickly aquifers are recharged and how water migrates beneath the surface, which is crucial for understanding the sustainability of our water resources. With this knowledge, water managers can make informed decisions to protect against overuse, prevent contamination, and ensure that communities have access to clean water for generations. Monitoring also helps detect pollutants early, so action can be taken before problems spread. By comparing isotope data, scientists can distinguish between young, renewable aquifers that refill quickly, and ancient, finite sources that took thousands of years to form. This distinction is vital for planning how much water we can safely use without depleting these precious reserves. Thanks to these scientific methods, we can keep our water supplies clean, reliable, and available for everyone, now and in the future. In the oceans, thorium-230 and protactinium-231 help scientists map currents and understand past climate shifts. By measuring these isotopes in deep-sea sediments, we learn how ocean circulation has changed over millennia. This knowledge helps predict future sea level, climate, and dan. Matrendo dab ostanen. Dapilem. Radioisotopes are vital for safeguarding our oceans and planet. Today we saw how radioisotopes are essential tools for tracing pollution dating events and tracking global cycles. If you want to learn more, check out one of e-learning platforms and follow us online. Thanks for joining me, Teacher Ivan. Keep exploring and stay curious.